Hi everybody, I am Pani Fernando from University of Sri Jayawardhapura, Sri Lanka. First of all, I want to thank SIMPA ICTP Fellowship to actually give me this opportunity to conduct a short course in nonlinear filtering theory. So let me write down the title of the short course. Introduction to nonlinear filtering theory and particle filtering. Okay. So this course actually we can actually divide it into 4 sections. In the first section, I will gonna describe the problem formulation of the filtering. Problem formulation. Then second topic is change of measure. And third topic is derivation of filtering equations. And last one is just an introduction to particle filtering. If time permits, we can discuss about this introduction to particle filtering. So the main reference of this course actually is the book by Girsanov and introduction to stochastic filtering theory. So this is a very nice book and a very readable book. So actually my short course actually mainly based on this theory in this book. So all right, so let's start with the problem formulation. So so what is nonlinear filtering theory means? So let's say we have a dynamical system, right? Dynamical system that we are not able to track the state of this dynamical system directly, right? We cannot track, unable to track the state of the system, right? Unfortunately. But on the other hand, we have some partial observations regarding on this dynamical system. So our goal is to actually use that partial observations to construct or predict the state of the unobservable dynamical system. Okay, that is the just a rough idea about the nonlinear filtering. So that means there are 2 stochastic differential equations, right, associated with filtering problem, right? There are 2 stochastic differential equation associate with the filtering problem, right? First one, so we have a governing stochastic differential equation actually. associated with the system, that is called signal process. Right? Signal process. Right? This is the one we want to predict. Right? Predict. Because we are unable to track the state of this dynamical system directly. So we want to predict this. So there is another equation that is called observation process, right? Right? So this is the process that, right, provides the information about the signal. Signal process, right? So we have two equations, basically, signal process and observation process. So we have some partial informations that is we acquire from observation process associated with this signal process, right? So using this partial information, we want to construct or predict the state of the signal process, right? So that is the rough idea about the filtering problem, right? For our convenience, we actually consider one-dimensional system, right? For the one-dimensional stochastic differential equation as a signal process, as well as one-dimensional stochastic differential equation as observation process. So let me actually write down our two equations. So first of all, let us take our probability space, right, as this, the filtered probability space, right? Right? Then we can define, we can state our signal process like this. So dxt equal alpha xt dt plus beta xt dwt plus gamma xt ddt, right? So this is signal process. So let's say this is equation 1.1, right? This is signal, right? This is the governing equation that describes the dynamics of the unobservable system. So which is actually perturbed by two Wiener noises, Wt and Bt. They are independent. Okay. Okay. Here, W and B are two independent 1D Wiener processes. All right. So the second equation is the observation process, dyt equal h of xt, right, dt plus dwt. So let's say this is 1.2. So this is the observation, right? This is the equation that actually gather the information associated with the signal process. Okay, right? So now we have two stochastic differential equations which describe the our problem, filtering problem, right? Now let's discuss about how to estimate, right? Using this information associated with the observation process, right? And the state of the dynamical system, that is xt, right? So before that, we need to prescribe some assumptions regarding on our coefficient functions, right? So let me quickly prescribe these assumptions, right? Assumptions. Point 1, we assume that, right, the mappings alpha, beta, gamma, and H are bounded and Lipschitz continuous, right? So every, I mean, all coefficient functions are very nice functions. They are bounded at Lipschitz continuous. That is, that means, right, there exist positive k such that for all xy belongs to R, maximum of alpha x, x, gamma x, and h of x is bounded. And also, the Lipschitz continuity gives us maximum x minus alpha y, beta x minus beta y, bounded by k, right? So now we have prescribed the assumptions regarding on coefficient functions, all right? So now we can actually prescribe the information we gathered from the observation process as a sigma field, right? Right? So we can denote, right, curly G of t as the sigma field actually generated by the observation up to time t, right? So GT actually contains all the information we gathered from this observation process, right? So now, so our goal is to estimate the signal process based on this information, right? Our goal is to estimate the signal, right, process xt, right, based on the information GT, right? This is our goal. So now we can ask a question. So what is the best estimate of the signal process based on this information that we gathered from observation process YT? That means, in other terms, the sigma field GT, right? What is the best estimate, right? So we can ask this question: what is the best estimate of xt given g of t, right? So it is well known that, right, the conditional expectation, right, conditional expectation of xt given the sigma field gt is the best estimate in terms of the, right, least square error, right? So we know that, right? Conditional expectation of xt given gt. So that is the best estimate, right? Best estimate of xt given gt is conditional expectation of xt. So this is the time, right? So so let's try to verify this, right? Let's try to verify. So I just want to note that so in this short course, that theorems and lemmas and propositions, I'm planning to prove all the theorems and propositions, because I want to make this short course as self-contained. Maybe sometimes some theorems and lemmas probably very easy for you guys, but it's better to prove these theorems and lemmas. So so let's try to verify this. So the following lemma certify this argument, right? Okay. So let me write down this lemma. Let me write down like following lemma certify the above argument. Okay. So what is the lemma? Lemma 1.1. So let's say z be a square integrable random variable in the probability space omega ft, right? And let curly G be a sub sigma field, okay? Sub sigma field of F, right? Then conditional, expectation of the square of the error in between Z and the projection of Z over the sigma field G, right? Actually minimize the error among Z and the square error among Z and the all G measurable random variables, right? If we can prove this, then we can actually certify that conditional expectation is the best estimate for the xt based on the information GT, right? So because that this candidate actually, right, this candidate actually minimize the least square error among the G measurable random variable. In particular, in this lemma, we consider the random variable, but random variables. But here we have random process. But it's a similar idea, right? So let's try to prove this result, right? Here, lambda is a square integrable G measurable random variable, okay? Now, proof, right? So, so we pick a lambda, arbitrary lambda from this space, G measurable square integrable G measurable random variable, and consider this difference, right? Z minus lambda square minus expectation of Z minus conditional expectation of Z given G, right? So we are going to consider this difference. If you can show that this difference is non-negative, then you are done, right? All right. So this is nothing but, because expectation is a linear operator, this is nothing but Z minus lambda squared, expectation of Z minus lambda squared, and Z minus expectation of Z given sigma field G square, right? Now you can apply the difference of two squares, right? And factorize it. So you will get, right? Expectation of Z given G, right, minus lambda times, right, 2Z minus lambda minus conditional expectation of Z given G, right? Okay, so we factorize it. Now what we are going to do? So now we are going to apply law of iterated expectation, right? That in other words, Tower property. That means here we have expectation. So now we are conditioning inside with respect to sigma field G using a law of iterated expectation. So we can call Tower property. Using Tower property, so you would get expectation of G lambda given G right. So we condition inside, right? Now you can see that we have conditioning inside, right? You can see that this guy, expectation of Z given G. So this is a G measurable random variable. On the other hand, lambda is also a G measurable random variable. Therefore, you can pull out this factor outside from this conditioning with respect to sigma field G. Then you would get, right, expectation of conditional expectation of Z given G minus lambda, right? Conditional expectation of 2Z minus lambda minus conditional expectation given G, right? All right. Okay, now we are in good shape. And since conditional expectation is a linear operator, right? So this gives us actually 2 times conditional expectation of Z given G, and lambda is a G measurable random variable, so lambda is remaining, right? Here we have, because this is again a G measurable random variable, so it's remain as Z given G. So this is actually boiled down to conditional expectation of Z given G minus lambda, right? So this factor actually reduced to conditional expectation of Z given G minus lambda. And here you have that term appears in front of that. Then basically you have expectation of conditional expectation Z given G minus lambda square, right? So this is non-negative, right? So we are done. So that means this difference is non-negative. So that means this candidate actually minimizes the least square error. Therefore, this is the best estimate for the signal process based on information GT actually gathered from the observation process, right? All right, so now you know the conditional expectation actually provides us the best estimate, right? So now we have to study about this conditional expectation, because that is the candidate that we have to focus on. So in practice, we are interested to estimate of the state process xt as a, estimate the moments of the state process rather than just focusing on the state process xt itself, right? So that means we are interested to study conditional expectation of f of xt given gt, right? With f belongs to rich class of functions, right? Class of functions. Which class of function? That means you can take f as twice differentiable bounded continuous function. Rather than just focusing on the conditional expectation of xt given gt, we are interested about the moments of xt. That's why we pick some nice function, right? So now let's denote the corresponding conditional probability distribution associated with this conditional expectation as pi t, right? Let pi t be the corresponding conditional distribution associated with this conditional expectation, right? Be the conditional probability distribution of this kind. Right? Okay. So this is the probability, conditional probability distribution, right? So this conditional probability distribution actually satisfy certain properties, right? All right, so let me point out those properties, right? So here phi t is a map from Borel sets on R plus omega 0, 1, right? Right, is a map satisfy the following properties, right? What are those? Right, first one, for fixed omega, right? This is a probability measure. On R, right? For all A belongs to this. A is a Borel set, right? This is a probability. I'm sorry, for all omega belongs to capital omega, right? We fix omega. I'm sorry. Okay. When you fix the omega, this actually behave like a probability measure on R. The second property, when you fix A, right, is a GT measurable random variable, right? It's a GT measurable random variable for all Borel set A. Right. Okay. The third property is phi t, the omega, nothing but conditional probability xt belongs to A given gt omega for all A belongs to A be a Borel set almost surely. Okay. Right? So pi t actually satisfy these three conditions. It's the conditional probability density associated with the guy that we want to study, conditional expectation of f of xt given gt, right? All right. So now actually let's see how to express this conditional expectation of f of xt gt, f of xt given gt in terms of integral with respect to this conditional probability density, right? So next, here actually we are going to introduce, right, a lemma which describe how to express the conditional expectation right, expectation as a integral of function f with respect to conditional probability distribution, right? Distribution. So this lemma is very crucial. So let me state the lemma and then we can sketch the proof. Okay. Lemma 1.3 for any bounded continuous function and negative t, we have conditional expectation of f of xt given gt, right? It's nothing but integral r of x pi t dx omega. So we actually represent this one as a duality pairing as f pi t right. So this is the result. So we can represent this conditional expectation of f of xt given gt as an integral with respect to conditional probability density. Okay. So let's see how to argue this. Argue the proof of this lemma, right? So we can sketch the proof quickly, right? Proof. So first of all, we consider our function f being a characteristic function, right? Be a characteristic function with A being a Borel set, right, in R. Okay. Then consider this integral, right? Let's write like this way, pi to f, right? So this is nothing but integral of this characteristic function, right, over A with respect to this conditional probability density. So this reduced to the integral over set A omega, right? So what is this? This is actually conditional probability density actually evaluated over the Borel set A, right? Okay. So this is nothing but this probability xt belongs to A given gt omega, right? It is straightforward. Okay. Simple calculation. So you can rewrite this conditional probability as again a conditional expectation by actually focusing the corresponding characteristic function standing on the Borel set A, right? This is, you can rewrite, re-express as right. So we have established for this the case where function f being a characteristic function, we have established the result, right? The conditional expectation of here our function f, right? Conditional expectation of f of xt given gt is nothing but this integral. For this simplest case, f being a characteristic function, we established the result. So next step, so you have to consider the f being a simple function. Now we consider a simple function f of x so 1 to n ai like this way, where these ai's are real numbers for I run from 1 to n, and these AI's, capital AI's are pairwise disjoint Borel sets, right? It covers whole set R, right? Right? And yeah, they are disjoint. Disjoint each other. Okay. So for this case also, we can actually carry out the argument by similar fashion that we establish for the case where f being a characteristic function, right? It's also very straightforward proof for the case where f being a simple function, right? Right. So just follow the same steps in steps for the case where f being a characteristic function to get the result for the case where f being a simple function. Okay. All right, that is straightforward. Now, for any non-negative bounded function, what we have to do, right? Function f, we can actually construct, right? We can construct a sequence of simple functions, right? Which converges to f pointwisely, right? Right. Then you can establish a result, right? Okay, using monotone convergence theorem, right? Right. For the last step, right? For any general bounded continuous function, right? For any bounded continuous function f, right, can be expressed as difference of non-negative continuous functions, right? In other words, the positive part and the negative part of the function f, right? So then immediately we can actually prove for any general function using the argument that we establish over here, right? So that is the proof, right, of the lemma 1.3. That means we can actually express the conditional expectation of f of xt given gt as a integral of function f with respect to corresponding conditional probability density function, right? Right. So come to your mind then, since conditional expectation of f of xt given gt, this is the quantity we want to study. Actually, we can represent as like this, right? So basically, we want to study about this conditional probability density by t, right? Because we can express this conditional expectation as an integral of f with respect to conditional probability density, right? So now onwards, we are just focusing on corresponding conditional probability density, right? Right. So in order to do that, so let us denote curly P of R be the collection of all Borel probability measures, right? We actually take curly P of R as the collection of all probability measures associated with the R, right? Right. Then immediately you can see that, right? Then the conditional probability measure pi t measure pi t, you can state as a process, right? Pi t is a PR valued, right? Measure valued, right? PR probability measure valued stochastic process. Right? Okay, so you can immediately see that this process conditional probability measure pi t when time evolves. So this is a probability measure valued stochastic process, right? So based on our discussion, we can see that pi t, right? Pi t is the optimal filter pi t is the optimal filter of our signal process. Pi t is the optimal filter, okay, our signal process. So now we want to study about this, right? Conditional, that conditional probability density associated with the conditional expectation f of x t given gt. So we can actually view that guy as a probability valued stochastic process, and it is the optimal filter. So we want to study about that. Okay. So it is well known that this optimal filter pi t is actually a solution of nonlinear equation called Kushner-Stratnovich equation, measure valued equation, okay, which is a we have to make sure that I have to actually stress about that this pi t actually solves nonlinear measure valued equation, right? The optimal filter pi t of signal process xt, right, solves the famous, right, Kushner-Stratnovich equation, and also people called FKK equation. FKK means Fujisaki-Kallianpur-Kunita equation. So So this is actually a nonlinear measure valued equation. Okay. This is a nonlinear measure valued equation. It's kind of hard to tackle, right? Because of the nonlinearity of this equation. Thanks to work by famous mathematician Zakai, right? We have a linear version of equation, but which solves some unnormalized filter. Okay. So actually, in 1960s, Zakai actually came up with this new equation, which is called Zakai equation, which is a linear equation, and which solves some different form of this optimal filter. We call this, that is, as a unnormalized filter. But the beauty of this result is this unnormalized filter and this normalized filter pi t are related each other based on famous formula called Kallianpur-Striebel formula, which is actually a kind of a generalized version of Bayes formula. So we will going to actually discuss about this Kallianpur-Striebel formula extensively. Actually, I'm going to prove that Bayes formula, then we can immediately discuss the proof of Kallianpur-Striebel formula. Then you can see the relationship between this unnormalized filter and optimal filter pi t, right? So, so in this course, in this short course, we first derive the Zakai equation, right, for unnormalized filter of the signal process xt, right? Then we derive FKK equation, Kushner-Stratnovich, in other words, FKK equation, which solves normalized optimal filter let me write over here pi t. Okay. So first of all, we are going to derive the Zakai equation. Then you can immediately derive the Kushner-Stratnovich equation by using the Kallianpur-Striebel formula. Okay. So that is the plan in the next lectures, and today also we are actually going to start. So before we are going to talk about the derivation of Zakai equation, we need, several tools to do that, because we need to actually come up with a new probability space with a new probability measure. Under that new probability measure, our observation process becomes a standard Wiener process. Once it becomes standard Wiener process, we can derive this linear Zakai equation under this new setting. So to discuss about this new probability measure and everything, so we need to discuss about the change of measure formula and everything, right? So let's start to discuss about that. So second chapter. Change of measure. So we are going to set up the environment now to discuss the derivation of Zakai equation. All right. So in order to derive Zakai equation, that solves unnormalized optimal filter, right? Unnormalized optimal filter. We need to obtain a new probability measure Q, right? Q, such that the observation process, I guess you remember what is the observation process. That is actually gather all the information about the signal process. Observation process becomes a standard Wiener process. Under the new probability measure Q. Okay, right? So in order to do that, let me provide you a couple of definitions, because we have to construct this new probability measure Q using the original probability measure P, right? So, to do that, we need this couple of definitions. Definition 2.1, a real valued process MT is a local martingale, right? It's a local martingale if there exists a sequence of stopping times tau n increasing to infinity almost surely, such that the n, this is nothing but the stopped martingale, is a martingale for all states. That means if you have a real valued process MT is a local martingale, so we call this a local martingale. If there exists a stopping time, right, tau n, such that this is increasing to infinity almost surely, then the stopped of this local martingale, process or associated with this real valued process is a martingale. Then we call this a local martingale, right? So this is the first definition. The second definition. Before that, let me denote these two classes, right? Let C lock and C2 lock are the sets of all continuous local martingales, right? Local martingales and continuous locally square integrable martingales respectively. Right. So these two classes actually denoted by first one is the class of all continuous local martingales, and the second class is C2 lock actually represent the class of continuous locally square integrable martingales. Okay. So let me state the second definition. Definition 2.2. For M belongs to square integrable continuous local martingale class, with M0 being 0, we define, right, E, curly E of M T as the exponential of MT minus 1/2 of the quadratic variation of M, right, for T positive, right. So curly E of M is given by this exponential process. So M is a square integrable local martingale. So what is this curly E? All of you guys know this is called famous Boolean dead exponential, right? So T let's represent like this. Curly EMT is called Boolean dead exponential. Right, this is called Boolean dead exponential. Right, you will see why we need this. Right, because this Boolean dead exponential, we need to define the new probability measure Q, right? Under that new probability measure Q, our observation process becomes standard Wiener process. Okay. The following theorem, right? Following theorem provides the criterion that this Boolean dead exponential process becomes a continuous martingale. Right? So we know that it is a local martingale. Yeah, we take M as M being the square integrable local martingale, but we can verify that M is just a local martingale. So now we are going to actually provide a theorem that which establish that this Boolean dead exponential process becomes a continuous martingale under certain condition, right? So let me state that theorem. Theorem 2.3, right? Kasamaki's theorem. Kasamaki's criterion, right? So let M being a continuous local martingale, assume that supremum over all stopping times, negative, non-negative stopping time tau, expectation of exponential of 1/2 m tau is finite, okay, where the supremum is taken over all bounded stopping times. Then this Boolean dead exponential process, right? Is a continuous martingale. Is a continuous martingale, right? It's a continuous martingale. So this actually proof of this theorem I am going to omit because actually I am going to use this theorem to establish kind of a weaker notion than the Kassamakis criterion to establish that this Doolean dead exponential process is a continuous martingale. So what is that criterion? Probably all of you guys know about that criterion, which is called Novikov criterion, right? Or Novikov condition, right? So theorem 2.4 Novikov's criterion, right? Novikov criterion. This is the criterion we actually use, right, for our problem setting. So this is a kind of a weaker notion than the Kassamakis criterion. So let M being a square integrable continuous martingale, right? Locally square integrable continuous martingale, and assume that expectation of exponential of the quadratic variation of M, 1/2 of the quadratic variation of M, is finite for all non-negative t. Okay. Then we have our Doolean dead exponential process being a continuous martingale, right? Martingale. Good, right? So we can actually easily prove this theorem by using the Kassamakis criterion together with the caveat given in the theorem, right? So let's briefly discuss about the proof of that Novikov's criterion, right? All right. Proof. So you can actually choose M being a square integrable local martingale, right? M belongs to C block with tau the bounded stopping time, okay? Bounded stopping time. Right. Then we have the Doolean dead exponential MT stopped Doolean dead exponential with respect to the stopping time. Tau is nothing but exponential tau half So now you can take the square root both sides, right? Once you take the square root, so you pick up here 1/2 and here 1/4, right? So this implies that, right? This implies that exponential of 1/2 of stopped process tau, right, equal to square root of the Julian-Dade exponential times exponential of, right, 1/4 of quadratic variation of the m, right? You have this. Okay. So next, so now actually we can apply Cauchy-Schwarz inequality to obtain, right, expectation of exponential of 1/2, right? So you take the expectation both side, and right hand side also you have expectation. Then you apply Cauchy-Schwarz for this guy, right? So then it becomes so equal square root of expectation of Julian-Dade exponential, stopped Julian-Dade exponential, right, times square root of expectation of exponential 1/2 right, this. So we have this result. So according to the hypothesis, right, we know that M is locally square integrable martingale, right? And therefore this is finite, right? Right. So according to the hypothesis, right, expectation of exponential 1/2 t stopped process of this quadratic variation is finite. And also we notice that, right, and also expectation of Julian-Dade exponential, stops Julian-Dade exponential, it's finite. Why is that? Since tau is a bounded stopping time, right? Bounded stopping time. Right? So this gives us, so this actually immediately gives us this left-hand side of this inequality is finite, right? This gives us that expectation exponential of 1/2 m stopped process, right, with respect to the stopping time is finite for any bounded stopping time tau, right? So we have this. Now you can take the supremum over this stopping time tau, right? Then you have the bounded this finiteness. Then what we can apply? So remind the criterion of the, remind the hypothesis associated with the Kasamaki's criterion. That is actually supremum over, right? Supremum over bounded stopping times tau. This quantity is finite. Then, right, the corresponding Doolean date exponential is a continuous martingale. That is what Kasamaki criterion established. So using Kasamaki criterion, because here we have proved that the hypothesis of the Kasamaki criterion actually established. Then by applying Kasamaki criterion, we can, by applying, right, Kasamaki criterion, we can conclude the proof, right, of the Novikov's criterion, right? So that is the simple proof of Novikov's criterion. So now we know what is the condition we have to check to satisfy corresponding Doolean date exponential being a continuous martingale, right? Right. So so next, actually, as I mentioned, beginning of this chapter 2, we are going to actually set up the environment to derive the Zakai equation, right? So that is why we actually, discuss about this Novikov criterion, right? We need this to make sure that we need the Doolean date exponential is a continuous martingale, because we need that Doolean date exponential to define the new probability measure, right? Right? Associate with the observation process. Using the observation process, you will actually see that we will gonna construct Doolean date exponential, right? So that is why we discuss this. On the other hand, to derive the Zakai equation, we need Kallianpur-Striebel formula, right? In order to discuss the proof of Kallianpur-Striebel formula, we need to discuss the proof of Bayes formula. So next, actually, we are going to discuss the Bayes formula. So let me state the theorem, right? So now we are going to introduce the Bayes formula Bayes formula or theorem, let's say theorem, which is very useful to derive Kallianpur-Striebel formula. Striebel formula, right? So let me state the Bayes formula, Bayes theorem. 2.5, right? Formula. Let beta is an integrable random variable on the probability space omega ft, right? So our sigma algebra is curly F, and curly G be a sub sigma field of F, sigma algebra F, right? Right. Suppose that Q be another probability measure, measure such that, right? So our original probability measure P is absolutely continuous with respect to Q. Okay. Okay. And M denotes the Radon-Nikodym derivative of P, probability measure P with respect to Q, right? Then we have, okay, conditional expectation of the random variable beta. Actually, beta is a F measurable random variable, okay, in the original probability measure P, given the sub sigma field G is nothing but, right, conditional expectation with respect to the new probability measure Q of beta times M given G over conditional expectation of the Radon-Nikodym derivative M with respect to new probability measure Q given G. So this is the Bayes formula, right? So here P is actually absolutely continuous with respect to Q, and later on you will realize that, I mean, once we apply this result for the Kallianpur-Striebel formula, and when we we have a few more theorems to to prove and discuss before we jump into the derivation of Zakai equation, you will realize that Q also is a probability measure that absolutely continuous with respect to P. They are more or less equivalent probability measures. Okay, so this is very crucial theorem to establish the Kallianpur-Striebel formula for the, it's kind of a generalized version. So I will continue tomorrow lecture with the proof of this Bayes formula. For now, I am going to stop the lecture. Thank you.